Hello all and welcome to lecture 17. We are going to look at the zeros of polynomials here, and we're kind of pulling this one out of chapter 4 just because it's something that you're going to use frequently. And it's really just an extension of what we did when we solved quadratics by factoring. So if you remember when we had our quadratic equations and we had our three strategies to solve them, one of those was factoring. And when you factored it, then you set each piece of the factor, right? Each factor equal to 0, right? And then solved for an x equals 0. And so what we're going to call those is we're going to call those the zeros of a polynomial, okay? So just like solutions to the equation, there are zeros to the polynomials. And so your definition here is that the zero of a polynomial, the zeros are values x equals. Now you can have more than one of them. In fact, you typically have as many as the degree of the polynomial. So if you have a cubic where your highest power is 3, you're looking for 3 solutions. So there can be many. So I'm going to call them C1, C2, C3, all the way up to Cn. Okay. And they can be anything, right? As long as they are real, they could actually be imaginary. Okay. Could be 0. Right? So these are values such that basically when you plug them in, you get 0. So so plug back into our function, any one of those C's. And I can say any one of those C's by saying C sub I. So I means any one of them 1 through n. And when you plug it in, you get 0. Okay. So that's what it means. A zero of a polynomial is just a value for x such that when you plug it in, you get 0. Okay, so we're going to go ahead and show in our example that x equals 1 and x equals 2 are zeros of the function x squared minus 3x plus 2, which means all we're going to do is take each of our x's and plug it into our function and show that that becomes 0. So we want f of 1, meaning we're going to plug 1 in for the x, and you're plugging that into this function over here. So that's 1 squared minus 3 times 1 plus 2. And if we simplify here, 1 squared is 1, 3 times 1 is 3, plus 2. And you've got 1 minus 3 is negative 2, plus 2 equals 0. And that one checks out. Then we're going to repeat that same process with our x equals 2. So f of 2 equals 2 squared minus 3 times 2 plus 2. And, sorry, I keep switching to my eraser. So 2 squared is 4, minus 3 times 2 is 6, plus 2, and 4 and 2 is 6, minus 6 gives you that 0 you were looking for. Okay, so all we're doing here is verifying that x equals 1 and x equals 2 are zeros of that function, because when you plug them in, you get 0. Okay, now why is this useful? Well, zeros of a polynomial are actually how it gets factored. Okay, so just like how we use the factorization to find the zeros when we factored quadratics, the opposite is also true. Okay, so if we have f of x as a polynomial, and a lot of this is just the mathematical technical language here. Polynomial degree n greater than 0, right? So that means you need something that has x's, right? X to the first, x to the second. And exist n complex imaginary numbers such that this. So basically, they can be real or they can be imaginary, okay? And you have n of them because your degree is n, and you should, right? That should match up. Where a is the leading coefficient of f of x, and each number is a 0. So basically, you've got an a sitting out front of here, and that allows for something to multiply by to change things. And then you've got x minus each of those zeros, right? Because that way, if we set each piece equal to 0, you would add your C1 or C2 to the other side, and you get x equals that value, okay? So that's why it happens. All right, each of those is a 0. Notice here we used a sub k instead of a sub I. It's the same exact thing, but you can create that factorization, okay? And so it allows us to create the function. So in example 2, it says find the function which has degree 3, has zeros x equals 2, x equals negative 1, and x equals 3. Now, you have 3 zeros here. Your degree is also 3. So that means we have exactly what we need. They each show up once. So that means our f of x is going to be equal to it. Now, I'm going to leave the A in that format from up above because I don't know what that A is yet. All I know is what my C1s and C2s and C3s are. So this is a C1, a C2, and a C3. The order does not matter whatsoever. Okay, you can put them in order, whatever order you want, and that's because multiplication is commutative. So order doesn't matter. So you've got x minus, and my first one is the 2, so x minus 2, times x minus the negative 1, and the x minus the 3. So what do we end up with? We have a times, and I'm just going to correct that or simplify the minus and negative to make that x plus 1 and x minus 3. All right, now the last thing we have to do is figure out what is this a value right here. And they did give us one more piece of information, and that's what we want to use next. So we have that f of 1 equals 5. So we're going to plug that in, and we're going to use that point to determine what our a is. So in that case, that means that this 1 is our x value, and this is our f of x value, right? So that means the 5 goes in place of the f of x, and I'm plugging a 1 in for the x's. So you have 1 minus 2, 1 plus 1, and 1 minus 3. And now we're going to simplify and solve for that a. So we have a times 1 minus 2 is negative 1, 1 plus 1 is 2, and 1 minus 3 is negative 2. So that is going to give us 5 equals. We have negative 1 times negative 2 is a positive 2. And positive 2 times 2 gives us 4a. And then I want a by itself, so let's go ahead and divide both sides by that 4. And that tells us that the a is 5 over 4. You can switch it to mixed numbers, but I wouldn't. I would leave that as an improper fraction. And all we're going to do is take that and plug it right back in up here. Okay? And that'll give us our final answer of f of x equals 5 over 4 times x minus 2 times x plus 1 times x minus 3. And that satisfies all the conditions here, because if you were to plug in a 2, right, you get a 0 in that first set of parentheses, and times everything makes it 0. Same thing for your other zeros. And then having the 5/4, if I plug in 1, I end up with 5. Okay, and so that's my final answer for example 2. Now, one other piece we want to talk about with zeros of polynomials is their multiplicity. If you notice in that last example, I had 3 zeros and they were all different. Okay, that doesn't happen every single time. It's possible that you get the same thing more than one time. And that's what we call its multiplicity. So if x minus c occurs m times, then c has a multiplicity of m. Okay, so when you factor, when you repeat factors, we can write that with powers. And so you'll notice right here that we have powers. And so the power on your parentheses or your factor is what's going to determine your multiplicity. Okay, so if we're looking at example number 3, it says find the zeros and state the multiplicity and sketch the graph. So my zeros come from each of these, right? So I've got this one, and this one. So I have 3 distinct zeros. So we have x minus 2 equals 0 will give us x equals 2. Okay, now the power on that is just 1, so this has a multiplicity of 1. We take our x minus 4, set it equal to 0. Add your 4 to the other side. That's going to give you x equals 4. And this time, that 3 as its power tells us that it shows up 3 times, so its multiplicity is 3. And lastly, x plus 1, set that equal to 0. Subtract your 1 to the other side gives you a negative 1. And that power there is a 2. And so that means it shows up twice. And so its multiplicity is 2. Okay, so far we found our 3 zeros. We've got 2, 4, and negative 1. And we found their multiplicity. The next thing it asks us to sketch the graph. So let's see if we can do that. Now, zeros are super useful because they help us to identify our graph. So we know that this has to be 0 at 2, 4, and negative 1. So we're going to go ahead and plot those points. So we've got 2, 4, and negative 1. So we know that we have to at least touch, if not cross through these 3 points. Now, if I look at my total, now this is some other things that we haven't super talked about, but let's do it now. If I add up all of the powers, so 2, 3, and 1, that gives us 6. When you have an even power, an even degree, that means that your endpoint, so where the arrows go on the left and the right, will both go in the same direction. Okay, if it's odd, they go opposite. One goes up to positive infinity, one goes down to negative infinity. So when you're looking at a positive a, okay, and the degrees are all an even number, it means you're going to start up here, right? And so typically what happens is that we are going to then come down and kind of wiggle our way through something like this. Okay. Now notice the odd ones I passed through, the even powers I kind of bounced off of. And that's pretty typical for these type of questions. Okay. But you want to connect to the top. Just a general sketch is totally fine. We're just looking for, see how it kind of creates the degree in the polynomial creates those curves or the wiggles, I like to call them. Okay. All right, and last one for this lecture, we're going to find the zeros of the polynomial. We've got a fifth degree here. And again, if we're going to find the zeros, that's linked to the factorization. It also asked me to find the factorization. So we're going to go ahead and start by factoring as much as we can. So if I'm looking here, I'm seeing that each term has at least degree 3. So that means I can factor out x to the third. And when I do that, I have x squared minus 4x plus 13 left over. Okay. Now, this one is already factored beautifully, right? My value here, if I set that equal to 0, is going to be x equals 0. It has degree 3, so it's x cubed, so that means it has multiplicity 3. So those are my first 3. And I'm looking for a total of 5 because my highest power is 5. So I'm missing 2 more, and that's going to come from this expression right here. And if I try to factor this, I'm looking for factors of 13 that add or subtract to negative 4. That's just not going to happen, right? 13 is prime. My only options are 1 and 13. So if I add them, that's 14. If I subtract them, it's 12, and I'm nowhere near 4. So I can't just factor this one, which means I'm going to have to go to quadratic formula because it is a degree 2 polynomial. So that means we're going to have x equals the opposite of b. My b is negative 4, so negative b is positive 4, plus or minus square root of b squared. My b is negative 4 squared gives you a positive 16 minus 4 times a, which is 1, so I'm not going to write it, times c, which is 13, all over 2a, which is just 2. So we have 4 plus or minus square root of 16 minus, let's see. So that's going to be 40, and 12 gives us 52 over 2. Subtract those. You can see right away this is going to be imaginary. So 52 minus 16, 52 minus 20 would be 32. Plus 4 would be 36. Oh, that's going to come out nicely. So that's a negative 36 over 2. And that's going to be this 4 plus or minus. The square root of 36 would be 6, but the negative under the square root means we get an I. So it's plus or minus 6i over 2. Okay, that's going to give us our last two solutions. So our other two zeros is going to be x equals 4 plus 6i over 2. Now we can go ahead and divide each of those by 2. That's going to give us 2 plus 3i. And the other one then will give us 2 minus 3i. Those are the two imaginary ones. Oops, sorry, flipped the screen on you. All right, and so those are both going to have multiplicity 1 because there's no power on that set of parentheses up there. And so now we're going to use that to write our complete factorization. Now there is no a value because there's nothing in front of our x to the 5th. There's just a 1 there, so our a is just 1. So we're going to have f of x equals, and we're going to have, oops, I don't need the parentheses because it's just x minus 0 is x to the 3rd. And then we're going to have x minus 2 plus 3i and x minus 2 minus 3i. If you want to go ahead and get rid of those parentheses, that's x minus 2 minus 3i and x minus 2 plus 3i. And that's my complete factorization. Okay, so I'm finding the zeros using any technique I have and then writing it out as a factorization. All right, on to the guided practice.